Well, hello everybody. Today we're going to discuss pipeline parallelism. And in previous chapters, we got to a point where we split our data by sequence inside of the attention. So that allowed us to decrease the activation memory. But we still have, and this is by the way a slide from our previous chapter. But we still don't know what to do when our model is really huge and it doesn't fit on a single GPU. Well, at least we already have a couple of options on how to decrease the required memory, but we haven't considered another option. What if we actually split model weights layer by layer onto different GPUs? And credit to this picture belongs to Gemini and Nana Banana. So without pipeline parallelism, which is exactly splitting weights of the model across multiple GPUs, well, we can't really fit a 70B model onto a single GPU, and even with 8B model, which we see on the picture, we already have quite high consumption when we do the training. And with pipeline parallelism, we don't address the activation memory. We don't address it at all, but we decrease the required memory for gradients, we decrease required memory for optimizer states, and for model parameters. And by the way, I'm not sure why we decrease required memory for gradients, but we'll talk about it later. So I'm not sure how accurate this picture is, but it certainly tells the right story about activation memory. So the claim from the book is that we don't decrease the activation memory because, since we split the weights onto multiple GPUs, say 4 GPUs, we're required to use only 1/4 of the overall memory for weights. But then the claim in the book is that nevertheless we will have to do 4 forward passes across 4 micro batches, mini batches, or whatever they call them, like they call them micro batches here. And we will wind up with the same activation memory, and it kind of didn't make sense for me initially, but then later on it kind of clicked. So I guess we'll get over that. But when I read it, that claim initially made me raise my eyebrows. Because in the first picture that we see, say we have 16 layers and we split them evenly across 4 GPUs. So we store first 4 layers on the first GPU, and etc. And that's what we get when we do forward pass and backward pass. And the math here is simple. Since we store only 1/4 of the weights on a single GPU, that means that we get activations only for 1/4 of the total activation memory, right? And that kind of doesn't align with this statement. But the problem with the current setup is that if we very naively split the weights across multiple GPUs and then wait for the forward pass and for the backward pass, we have these huge gaps. And that's not going to work in production. At least that's not going to efficiently work in production. So how can we optimize it? One of the first ideas is to interleave various batches, and here the numbers, they don't tell us which layers we have on the GPUs. These are the numbers of the micro batches. So imagine that you have 8 micro batches of data. It's like different sequences, 8 different sequences in batches of data. And then once we forward pass these 8 sequences through the first GPU, we immediately, well, almost immediately start doing the same on the second GPU for the next weights, right? So we, in this picture, we do the same split of the weights across 4 GPUs, and then for the first batch, we run it through the first 4 layers, then through second 4 layers, like layers 5 to 8, then for the third 4 layers, and etc. and etc. And this way we can parallelize our forward pass across multiple batches, and we can parallelize our backward pass, and we see that this so-called bubble of the idle time is much, much less. But with the current picture, we need even more activation memory, right? Because we split our weights in 4 chunks, but we have 8 micro batches. That means that we store 8 times of the activation memory, and our activation memory is only 1/4 of the total activation memory, so this picture didn't make any sense for me at all. And for a good reason, because it seems like, why do we even need like this 5, 6, 7, 8 batches? Because once we hit 4, we already shipped the first batch onto the 4th GPU, so it kind of, in my view, the diagonal should be much, much smaller. Like, we should cut it in half, and that's exactly what's proposed in the second picture, well, in the third picture, actually. So I don't even know why the authors of the book included this version, but nevertheless. So this is a less naive version of how we can interleave the batches, and we have 4 batches, and the number of batches is exactly the number of GPUs we split our weights across. And now our initial claim finally makes sense. So we can't really do any better in terms of parallelization, in terms of time efficiency and kind of gap efficiency, than winding up with the full memory of activation. Because if we don't do that, we get this picture where we have these huge bubbles, and if we want to reduce bubbles, one of the straightforward bets is to start doing the forward pass for the second batch while we processing the first batch on the second GPU. And that means that the least number of batches that we need to process is 4, because by the time our first batch hits GPU number 4, we're already processing the 4th batch. And this is not the final result. We can do a bit better. Well, not a bit better. We can do much, much better than this bubble size that we see in the picture. But this is kind of probably the good starting point of what we can do fairly easily. And it's easily to grasp and depict in mind. So the idea is that, once again, we have 4 batches. As soon as we process the first batch across the first chunk of weights, we ship it off to the second GPU in a ring-like fashion, and then we do the backward pass in similar fashion. And actually, we can even see that we interleave backward pass with some forward pass for the next batches. So it all makes sense, and probably I think that we can even interleave this forward pass here, right? So we probably can start doing this 9, 10, and 11, and 12 in these gaps if we have these gaps. It also depends on how much time we spend on calculating backward pass, how much time we spend calculating forward pass, and etc. and etc. But possibly we could kind of shift this 9, 10, 11, and 12 in these gaps as well.
Mm-hmm.
And in terms of throughput, we observe, well, a substantial decline when we go high in the pipeline parallel size. So I'm not sure what's the model size here, but for the model size that we had in the book, I reckon it's 8B, but I might be wrong here. So for some model that they analyzed, we observe with number of batches equal to 32, we observe a significant performance drop up to 52%. Now, yeah, and we kind of, yeah, we see different analysis of different micro batches, right? So it seems as if we decrease the number of micro batches by 1, so it's not like it doesn't equal the pipeline parallel size, it's a bit less. So we kind of probably can have better interleaving of like these small spaces. We can achieve better performance here, right? So cool. And this stuff is exactly, well, this stuff is exactly what's used for training Llama 3.1. But as we said before, it's fairly straightforward, but we can do even better. Our initial idea was to split the model weights sequentially. So like the red blocks go on the first GPU, like green is second, blue is third, and yellow is fourth. But what if we don't do it? We don't do it sequentially. What if we actually interleave our model weights? And if we had 2 GPUs, we can just send odd layers to the first GPU and even layers to the second GPU. If we have 4 GPUs, we can do something like this. So kind of we first sequentially split it across 4 GPUs, like the first half, and then we split the second half across 4 GPUs as well. And that means that when we do forward pass, we kind of pass it over to our first, like we run our data through the first 4 GPUs, and then we go back. So it's kind of it forms a cycle with multiple iterations, and that's what we wind up with. So here we can see in dark green the forward pass of the first layers, and then in light green forward pass for the last layers, and same deal with backward pass. And as we can see, this allows us to decrease the bubble size and to interleave some forward pass for the last layers with already started backward pass. They already gave us, they even gave us a fancy equation in the book. I don't think it makes too much sense to analyze this equation in detail. It's much more important to get the intuition that if we be a bit more smart about how we split the weights across multiple GPUs, we can efficiently fill these small gaps when we do backward pass. And activation memory is still the same, and as we said before, I don't think it's possible to decrease our activation memory if we want to be efficient here and efficiently fill all these gaps. But that's not the end. We can do even better. Let's think, and let's truly think what happens during backward pass. So during our forward pass, we do this matmul of our input by weights. We get the feed it to activation function, etc., etc. So we have a matmul, and we do pass it forward. During our backward pass, we actually calculate 2 gradients, right? We calculate a gradient for our weights, and we calculate gradient for our inputs. And to do backward pass, like the only thing that our previous layers need is gradient for layers. Our previous layers, they don't really care about our gradient for weights. So that means that we can first calculate this gradient, pass it over to our previous GPUs, or to previous layers, previous GPUs, and then while we have idle time, sometime later, we can calculate the second gradient. And that's exactly the idea of so-called zero bubble pipeline parallelism. So in our previous picture, we kind of we tried to be a bit more smart than before with well, actually no, this is very general picture when we let me see. I think it doesn't matter which one is it. I mean, in terms of how exactly we split the weights here. Like, is it sequential or is it like odd and even? The only thing that matters is that we have a huge bubble here, and we can't really do too much about this bubble. But if we calculate gradients for our weights a bit later, we can use this gradient calculation to fill in the gaps. And that's exactly what's depicted on the picture on the bottom. I think that's our most efficient variant. So when we do the forward pass, yeah, I think the difference here is that here the first the ZBH1 is the algo when we do this, so when we split the weights sequentially, and ZBH2 is when we split the weights with the gaps. And with our most efficient variant, we can see that maybe it just requires more activation memory, and we just kind of sacrifice activation memory for efficiency. I don't think it matters too much. The only thing that matters is intuition. That here we can see that first we did the forward pass, then we start doing backward pass for our inputs, and then we do the backward pass for our first layer. We pass it over to other GPUs, and then we do backward pass for the first layer for our weights, only much later on, right here, right? So we do backward pass for the inputs first. We interleave it here with the forward pass, and then we start doing backward pass in the gaps for our weights, and that allows us to have very small bubbles right here, only three squares. Here it's not a bubble, it's optimizer step.
Here the numbers are still representing the micro batches, right?
Yeah.
You trace number 1, for example, in the first picture, it goes for forward.
Yeah, so it's micro batch. For first goes forward, goes back,
and back
the
forward,
inputs,
and then starts to apply weights in the gaps.
Yeah, and I think like it's just for simplicity, it doesn't have to go sequentially. So for instance, I mean like it's weights, so it can happen at any point in time, right? As long as we have memory to store activations and gradients, input gradients, we can calculate backward pass for the weights even like here. The only problem is memory. But in terms of time, we can calculate backward pass for our weights at any point in time later.
Nice. And they are just stored until we do the optimizer and we actually apply the...
Yeah, so probably not here, like before optimizer state, before optimizer step. And it can be even more efficient. I think, once again, it doesn't really matter like the exact algorithm as much as intuition. So this is what DeepSeek R1 and, well, actually, I think it's from technical report from DeepSeek v3.2. So essentially, as we can see, they did the same thing. They did the forward pass in different micro batches. Then they start doing backward pass for input in green, and they interleave it with backward pass for weights, and they even delay backward pass for weights to some much later point in time. So as long as you have memory, you can delay backward pass for weights for a long time. And they even have this like fancy equations of calculated like predicted bubble size, and they calculate like rough estimations, maybe not so rough, estimations of memory required for the activations. And here we can see that we couldn't go down to anything less than full activation memory right here. And for their proposed approach, which well, seems they did better based on the equation. To be honest, I didn't like try to dig really deep into what happens here. Just wanted to get intuition behind the method. So they got even more activation memory, probably because they need to store activations to do these weights much later on. Yeah, so this was it. It was fairly straightforward and quick. So do we have any questions or comments?
So in the previous picture, there are some blocks without digits. The orange ones without digits. What are those?
Yeah, I think it's continued forward pass. So probably they split the batch in even further, and like they split the batch into two nano batches.
Right, is this where it's orange and green? I see it's overlapped.
Yeah.
That's fine, but what about the oranges in the very beginning on the left?
You mean like this stuff?
Mm-hmm.
Um, that's a good question. Um, well, I don't see. Well, we have 7 only here, so
Just to avoid visual noise.
probably I think they just wanted to communicate the idea. Not sure what this extra block is supposed to be doing, really.
And the shape is a bit weird, right? It starts from device 7 as well.
Maybe, you know what? I think it's not like the start of the algorithm. It's probably in the middle of pipeline somewhere. So maybe it's kind of the leftover from some.
A
Well,
step, but you have to be like when optimizers does a
yeah,
step, it
yeah. They
has to
don't.
like stop everything, no?
Um, I think so. Yes. So yeah, they also miss the optimizer state, optimizer step somewhere in this lines.
Uh-huh.
Yeah, well, it's a technical report. What can you do?
Pretty cool.
Anything else?
Does it combine easily with all the other parallelisms we have seen so far, or we will see it in the next lecture
Yeah,
how
I
it
think
all
it's going to
goes?
come in the well, lecture after the next one where we talk about combining it all together. Um, or maybe in the next one. I don't really. Yeah, I think it's
Mhm.
going to come after the next one. But I asked Claude the exact same question, and yes, I think the whole idea is to combine everything and to find the balance between throughput, between communication, between model weights, between activation memory. So yeah,
Mhm.
long story short, you can combine tensor parallelism, pipeline parallelism, and data parallelism
Mhm.
all at the same time.
Wow, this is super efficient, probably. It's all combined together.
Yeah, and super complex.
You can train probably very large networks. It's just, yeah. Hmm.
All
Very
right.
cool.
If we don't have any other questions, then I guess this is it.
Sounds good. Thank you so much.
Okay, let me stop the recording. And